Hello everyone, I would like to welcome you to today's lecture where we will continue with the discussion of the Fetison's reagent which we introduced last time. We saw that the Fetison's reagent, which is basically a adsorption of silver carbonate on the surface of silicate, and that allows different kinds of oxidations of primary, secondary, allylic as well as benzylic type of alcohols, and especially it is useful for the oxidation of a diol to form the lactone via lactol. So, last time what we were discussing about the various aspects of static factors and the polar factors. Towards the end I mentioned that an example of this kind, which basically has an alcohol which is having a double bond versus another alcohol in which no such double bond is present. So, this particular alcohol reacts much faster than this alcohol, obviously because there is a competition for the alcohol to get adsorbed on the surface of the reagent with the double bond, which also tries to participate to act as a kind of nucleophile for the surface of the Fetison's reagent. So, there is a competition between the double bond and the OH, and therefore, this particular alcohol reacts slower than this alcohol which is devoid of such a double bond. Due to the mildness of Fetison's reagent and its sensitivity to minor structural features, something I just mentioned, that if there is a double bond versus there is no double bond. Therefore, this oxidant, that is Fetison's reagent, is particularly well suited for the monooxidation of symmetric diols. Now, we have a symmetric diol like this here, and we can carry out a monooxidation, that means between the two of them only we can oxidize one of the alcohols, even if we use excess of silver carbonate, because it is slow reaction, and therefore one can monitor and stop when the oxidation of one of the hydroxy groups gets oxidized to the corresponding ketone. At the same time, we can also obviously take up an example where there is, say you have a hydroxy group which is secondary hydroxy group, and then we have another hydroxy group which is, say for example here, tertiary. So, if this is secondary hydroxy group and this is a tertiary hydroxy group, we can specifically oxidize this and it does not get oxidized. Obviously, it will not get oxidized because it is tertiary, but at the same time we can also take another example in which hydroxy group is secondary and at the next carbon you have another hydroxy group which is tertiary. Now, substrates of this kind have been found to have problems for the CC bond cleavage with other oxidizing agents such as chromium based or other oxidizing agents, but that does not happen in the case of Fetison's reagent, and what one easily can get is this type of hydroxy ketone without affecting the CC bond cleavage. Now, a Fetison's oxidation allows the preparation or obtention of the desired alpha hydroxy ketone of this kind. This is exactly what I mentioned before, that if we have a tertiary hydroxy group here and a secondary hydroxy group here, then the oxidation can lead to the alpha hydroxy ketone without any cleavage of the CC bond, whereas the Collins reagent PCC, pyridinium chlorochromate, pyridinium dichromate, produce an oxidative cleavage of the CC bond. Similarly, Jones and Moffat oxidations yield complex mixtures, whereas Cody-Kim oxidation does not give any oxidation and gives back the unreacted starting material. What it indicates is it is a mild oxidizing agent, and therefore it is useful for the oxidation of a substrate having a hydroxy group, which is a secondary hydroxy group and a tertiary hydroxy group here to form the alpha hydroxy ketone of this kind. Now, the following alcohol is oxidized with Fetizon's reagent in the presence of dialkoxyalkene. Now, this is example where we have this dialkoxyalkene. There is an alkene on which you have two of the alkoxy groups here present. So, therefore, this is a very reactive substrate, and of course, when it was reacted with PCC, there was cleavage and there was no oxidation of the alcohol. That means the CC bond was cleaved and there was no alcohol oxidation. On the other hand, Fetizon's reagent allows the oxidation to take place, even though the yield is low, still oxidation does take place, and the reagent allows oxidation of such a allylic alcohol, which is a sensitive substrate. Now we will move on to a new oxidizing agent, which is ruthenium tetroxide, or we can also use a combination of ruthenium trichloride and sodium metaperiodate. But let us first see what was initially done. That it was found by Carl Gerasi in 1953 that olefins can be cleaved, the CC bond can be cleaved using ruthenium tetroxide in carbon tetrachloride. This was found to be a very powerful oxidant, and it basically involves oxygenation and hydrogen abstraction. We will discuss about the mechanism a bit later. It is comparable with osmium tetroxide in terms of olefin dihydroxylation, which we will also discuss in a while, and it cleaves the CC bond to give ketones, aldehydes, or even acids. It is a very aggressive reagent, hence room temperature is good enough for the cleavage of the CC bond taking place. Halogenated solvents such as CCl4, dichloromethane are used because ether, benzene and pyridine react very violently with the ruthenium tetroxide. If one sees the structure of ruthenium tetroxide, then you have 4 oxygens attached to the ruthenium, and therefore the ruthenium here is highly electrophilic. Therefore, the ether, benzene and pyridine, all of them they react very violently with ruthenium tetroxide. Unfortunately, the yields of the products are variable, that means it depends on substrate to substrate, but at the same time it has been found that instead of using ruthenium tetroxide, if one tries to add sodium metaperiodate as a co-oxidant, the yields can be improved. What it means that the ruthenium tetroxide, when it oxidizes or cleaves a double bond, it gets reduced to the low valent ruthenium species, and that can be reoxidized using sodium metaperiodate. And that is where the efficiency of the reagent increases by the addition of sodium metaperiodate that acts as a co-oxidant in these reactions. On its own, ruthenium tetroxide is volatile and highly toxic and is also reported to be known as an explosive. The reaction therefore can be performed conveniently in a biphasic medium using ruthenium trichloride or ruthenium tetroxide in catalytic amounts. Since ruthenium tetroxide is an expensive reagent, people have tried to make use of other ruthenium source such as ruthenium trichloride or ruthenium dioxide in catalytic amounts along with co-oxidants such as sodium metaperiodate or periodic acid or sodium hypochlorite as co-oxidants. Ruthenium tetroxide is soluble in organic solvents and it is consumed in the reaction and moves into the aqueous layer as ruthenium dioxide. Ruthenium tetroxide, when it oxidizes the substrate or oxidatively cleaves the double bond, it forms eventually ruthenium dioxide, and therefore if one uses a biphasic medium containing an organic phase and an aqueous phase, and in the aqueous phase the co-oxidants such as sodium metaperiodate or sodium hypochlorite or periodic acid is used. So, when ruthenium tetroxide, which is soluble in organic solvent, oxidizes the substrate to the corresponding oxidized species, either CC bond cleavage or whatever, and in the process it forms ruthenium dioxide which passes to the aqueous phase, and in the aqueous phase the oxidant, the co-oxidant which is present reoxidizes the ruthenium tetroxide, ruthenium dioxide to go to ruthenium tetroxide. So, one can start with only catalytic amount of ruthenium tetroxide and this reaction can be done. However, initially Sharpless used ruthenium dioxide only as a reagent since it is cheaper than ruthenium tetroxide, and later he used ruthenium trichloride in place of ruthenium dioxide. So, right now a lot of people who want to use this protocol prefer to use ruthenium trichloride and sodium metaperiodate as a combination of reagent which is a source of ruthenium tetroxide. However, there are some problems which are observed. For example, if one takes the ruthenium reagents, so there are cases where it has been found that the reaction becomes slow and there is an incomplete reaction. Now, this happens in cases where carboxylic acid is formed. The sluggish reactions which are observed are due to the inactivation of ruthenium catalysts with carboxylic acids that form low valent ruthenium carboxylate complexes such as this. So, such kind of complexes with the carboxylate reduces the activity of the ruthenium catalyst, and therefore the reactions are slow and incomplete. At the same time, it was observed that the inactivation of catalysts like this can be prevented if we add acetonitrile as a solvent, or a molecule of acetonitrile now will have competition with the carboxylic acid or the carboxylate to form the complex that we saw, that forms with the carboxylate complexes. So, the nitrile blocks the site of the ruthenium species and does not allow carboxylates to form complexes. It only temporarily allows the site protection, and therefore the oxidation is completed. And for example, we can see here the CC bond cleavage of this double bond with ruthenium trichloride sodium metaperiodate in the presence of CCl4 and water gives 17% of the corresponding aldehyde and 80% of the starting material is recovered. On the other hand, if acetonitrile is used as a solvent, then one gets the 88% yield of the corresponding carboxylic acid and all the starting material gets completely consumed. So, therefore, the inactivation of the catalyst can be prevented if one adds acetonitrile. So, the protocol which is now generally followed is this protocol, in which one takes ruthenium trichloride and sodium metaperiodate in a reagent solvent system such as CCl4, water and acetonitrile, and then the oxidative cleavage occurs. Now, ruthenium tetroxide is powerful oxidant, and especially it is useful where, say for example, ozone, osmium tetroxide or KMnO4 type of reagents do not cleave the alkene. This is an example which is a tricyclopentanoid example, in which there was a need to cleave this bond, and this bond cleavage was not easily possible using the reagents such as ozone, osmium tetroxide and KMnO4, but ruthenium tetroxide, which is formed from ruthenium dioxide in presence of sodium metaperiodate, allows the cleavage of the CC bond to form this product in 53% yield. So, there are advantages of this reagent, and therefore, it is used in organic synthesis quite a lot. Interestingly, when you have a substrate of this type where there is a primary alcohol, and that primary alcohol under these conditions of ruthenium trichloride sodium metaperiodate allows oxidation to give the corresponding carboxylic acid in a very short time, such as 1 hour. Now, it is a non-selective oxidant. I have been telling all the time that the ruthenium tetroxide is a very violent or a very aggressive reagent, and therefore, it reacts with many other functional groups such as multiple bonds like double bond or triple bond, diols, aromatic rings, ethers, etc. Now, for example, here we take a diol of this type which undergoes a cleavage here to form eventually via the corresponding aldehyde the corresponding acid. So, there is no racemization or there is no rearrangement that occurs during this process. So, which is an advantage by using such a reagent, which is a bit of aggressive reagent, but then reactions are done at milder conditions, and therefore, there is no side products that are formed. Now, we have another example in which such a complicated tricyclic molecule can be converted to the corresponding carboxylic acid, which is normally difficult with using other oxidizing agents. So, this example simply illustrates that how the primary alcohol can be oxidized to the corresponding acid under these conditions. What exactly happens is, if we have the aldehyde, then the ruthenium tetroxide will react to form this intermediate, because we can write the ruthenium tetroxide under the water medium to be somewhat like this. So, the hydroxy group here attacks onto this aldehyde and you move this electron pair from there to form this intermediate, and that undergoes oxidation here like this to form the corresponding carboxylic acid, and during the process you release the ruthenium, low valent ruthenium substrate, which again of course reacts further. But it is interesting that when one carries out the reaction with a double bond, one can also stop the reaction at the diol stage, because this is the diol that undergoes further reaction and allows the cleavage to take place. So, this cleavage can be prevented if one stops the reaction at the diol stage by keeping the reaction time short. So, if one carries out the reaction say at 0 degrees and only allows within 5 minutes to check if the reaction can be stopped at the diol stage, so one can isolate the corresponding diol. So, this is an interesting observation which was published in 1984. That means that you have an alternative as compared to the osmium tetroxide to go to the corresponding diol, and if one wants this diol to be converted to the corresponding dialdehyde bond for the cleavage of the CC bond, then of course you can allow the reaction to go further for a longer time and the cleavage can take place. But getting the diol is also an alternative, and which is a good alternative for the reaction. Interestingly, a phenyl ring can also be cleaved to the corresponding acid, because an aromatic ring is basically nothing but having several double bonds. Since the ruthenium tetroxide is a very aggressive reagent, is a powerful oxidant, so even the phenyl ring gets oxidized to the corresponding acid. These kind of conversions of the aromatic rings or electron rich aromatic rings to the corresponding acids have been utilized in organic synthesis. Now, here we have another example in which we have a lone pair of electrons on the nitrogen blocked by the using of this protecting group, which is a Bock group, which is nothing but this kind of, where the lone pair of electron on the nitrogen is in conjugation with the carbonyl group. Therefore, the lone pair of electron here is not available for the oxidation, for the oxidant to give any problem, and therefore a substrate of this kind can be cleaved to the corresponding acid without any problem if one protects the nitrogen here as a N-Bock protection. So, the conversion of such substrates to the acid can also occur readily with using the ruthenium tetroxide formed in situ by ruthenium trichloride and sodium metaboride. It is also observed that if one uses a nitrogen ligand of this type, we can convert an olefin to the corresponding epoxide, which is interesting reaction, because the lone pair of electron on the nitrogen will react with the ruthenium tetroxide to form this species. Now, if this species comes in contact with the olefin, one can have a 2+2 cycloaddition of the ruthenium oxygen double bond and the double bond of the olefin here, forming this intermediate which can undergo a cleavage forming the epoxide and low valent ruthenium species. So, this is one of the very rare examples of for conversion of olefins to the corresponding epoxide, but nevertheless one can carry out such a reaction in the presence of nitrogen ligands. Essentially what they do is to reduce the activity of the ruthenium tetroxide by this particular nitrogen ligand. There is another important reaction which is conversion of ethers to the esters, corresponding esters, or to lactones. So, if we have an ether of this kind, one can get the corresponding ester. If one starts with a cyclic ether, one can get the corresponding lactone. In a similar fashion, this cyclic ether goes to the corresponding lactone. Even this type of cyclic ether having many functional groups and a site where there is a possibility of lactone formation can allow the lactone formation to take place. Now, why should this happen? This happens mainly because, as we have discussed earlier, that ruthenium tetroxide is a very powerful oxidant, and we cannot use solvents such as ether or pyridine or benzene, such solvents, because they can also react. This is precisely the reason why ethers can form the corresponding ester, or the cyclic ethers can form the corresponding lactone. Now, we will stop at this stage today, and in the next class we will try and see what is the mechanism by which these ethers, which are acyclic or cyclic ethers, are converted to the corresponding esters or lactones, and further developments of the ruthenium reagents for other reactions that we will see. You can go through these notes and then get ready for the next class. Till then, goodbye and thank you.